Welcome! In this session, we'll explore problem number 1268, Search Suggestions System. This problem is a great opportunity to delve into efficient string searching techniques and explore how to optimize algorithms for autocomplete functionality. Let's dive in. In this problem, we need to design an autocomplete system that provides search suggestions based on a list of product names and a search query entered by the user. The way this works is that as the user types the search word, the system will generate a list of suggestions for each prefix formed by progressively adding one character at a time. These suggestions should be derived from the given product list, and they must be sorted in lexicographical order. Each prefix can return up to 3 product suggestions. For the input format, we have 2 key components. First, a list of strings called products, which contains the product names, all in lowercase English letters, and second, the search word, which represents the query being typed, also in lowercase. The output will be a list of lists, where each inner list contains up to 3 products matching the current prefix of the search word, sorted lexicographically. Let's look at an example to understand this better. Suppose the list of products is mobile, mouse, moneypot, monitor, mousepad, and the search word is mouse. For the first prefix, M, the system identifies all products starting with M, which are mobile, moneypot, monitor, mouse, mousepad. Out of these, the top 3 products in lexicographical order are mobile, moneypot, monitor. For the second prefix, MO, the matching products remain the same, so the suggestions are still mobile, moneypot, monitor. For the next prefix, MOU, the matching products narrow down to mouse, mousepad, and since there are only 2 matches, both are included. Similarly, for the prefixes mouse and mouse, the matching products stay as mouse, mousepad. The resulting output is a list of lists, where each inner list contains the suggestions for the corresponding prefix. To elaborate further, when the prefix is extended to MO, the matching products are still mobile, moneypot, monitor, mouse, mousepad, and the top 3 suggestions remain mobile, moneypot, monitor. For the prefix MOU, the system filters the products to only those starting with MOU, which are mouse, mousepad. Since there are only 2 matches, both are included in the suggestions. The prefixes mouse and mouse produce the same 2 matches, mouse, mousepad, as no additional products meet the criteria. Now, let's consider another example to see how the system behaves with different inputs. If the product list contains only Havana, and the search word is also Havana, then for every prefix, from H to Havana, the only matching product is Havana. The output for this example would be a list of lists, where every inner list contains just the single product, Havana. Here's another example to explore more cases. If the product list is bags, baggage, banner, box, cloths, and the search word is bags, the system processes each prefix of bags to generate suggestions. For the first prefix, B, the matching products are baggage, bags, banner, box, and the top 3 in lexicographical order are baggage, bags, banner. For the prefix BA, the matching products remain the same, so the suggestions stay as baggage, bags, banner. For the prefix bag, the system narrows down the matching products to baggage, bags, both of which fit within the top 3 limit. Finally, for the prefix bags, there's only one matching product, bags, which becomes the entire suggestion for that prefix. This demonstrates how the system dynamically adjusts the suggestions based on the current prefix. Now, let's discuss the constraints and edge cases to keep in mind while designing the solution. The product list can contain up to 10,000 items, and each product name can be as long as 100 characters. Similarly, the search word can also have a length of up to 100 characters. All strings in both the product list and the search word consist of lowercase English letters, and all product names are guaranteed to be unique. For edge cases, consider situations like when no products match a given prefix. In such cases, the output for that prefix should be an empty list. For example, if the products are apple, banana, and the search word is car, then the output for each prefix of car would be empty lists. Another edge case is when there's only one product in the list. In this scenario, that single product should be the suggestion for every matching prefix. Additionally, we must ensure that the solution handles very large inputs efficiently. For instance, if the product list contains the maximum number of 10,000 items and the search word is long, the implementation should still run within a reasonable time. Another edge case to consider is when the search word generates prefixes that match exactly one product. For example, if the product list is Apple and the search word is app, the output should consistently provide Apple for all prefixes that match. These scenarios highlight the importance of optimizing the solution to handle edge cases and constraints effectively, ensuring accurate and efficient results even for extreme inputs. To start, let's consider the brute force approach. This method begins by sorting the products list to ensure that any matches we find are already in lexicographical order. Then, for each prefix of the search word, we iterate through the entire products list to identify items that match the current prefix. Once we have these matches, we take the smallest 3 products and add them to our output list for that prefix. While this approach is straightforward and relatively easy to implement, the inefficiencies arise because we repeat the prefix matching process for every single prefix of the search word. This results in a time complexity of n log n for sorting the products initially, and m*n for iterating through all prefixes and products. The overall complexity, n log n plus m*n, becomes prohibitive as the input size grows. Additionally, the space complexity is n plus m, where n accounts for the sorted products and m for the output list length. While the brute force approach is simple, its inefficiency makes it unsuitable for larger input sizes, as it involves repeated full list scans and redundant computations. Now, let's explore an optimized approach using binary search. The idea here is to leverage the sorted order of the products list to quickly locate the range of items matching a given prefix. For each prefix of the search word, we perform a binary search to find the starting index of matching products. From this index, we collect up to 3 products, as long as they fall within bounds. This eliminates the need to repeatedly iterate through the entire products list. The time complexity improves significantly, with n log n for the initial sorting and m log n for performing binary search on each of the m prefixes. Collecting up to 3 products is constant time, resulting in a total complexity of n log n plus m log n. In terms of space, the complexity remains n plus m. While this approach is more efficient than brute force, it introduces some added complexity in managing indices and ensuring we collect the correct products. Nevertheless, binary search is a significant step forward in optimizing prefix matching efficiency. Next, we turn to the tree-based solution, which offers even greater efficiency for prefix matching. A tree, or prefix tree, is a hierarchical data structure where each node represents a character. As we build the tree, we insert each product into the structure, updating nodes to maintain a list of up to 3 lexicographically smallest products for the prefix ending at that node. Once the tree is built, searching for matching products becomes extremely efficient. For each prefix of the search word, we simply traverse the tree to the node representing that prefix and collect its list of products. This approach eliminates the need for repeated full scans or binary searches altogether. The time complexity here is n*k for building the tree, where k is the average length of the products, and m*k for searching through the prefixes of the search word. The total complexity is n*k plus m*k. By pre-processing the products into a tree, we achieve fast and efficient prefix lookups, making this an excellent choice for implementing a search suggestions system. The space complexity of the tree-based approach is n*k, where n is the number of products and k is their average length. This accounts for the memory needed to store the tree structure and the associated product lists at each node. While the tree offers unmatched efficiency for prefix matching, it does come with the trade-off of higher memory usage and a more complex implementation compared to the other approaches. However, when considering the overall strategy, the tree emerges as the most suitable choice. By pre-processing the products into a structured format, we minimize the time spent on repetitive prefix searches. With constraints that allow for up to 10,000 products, the tree's ability to efficiently handle real-time lookups becomes invaluable. The key insight here is recognizing that hierarchical organization through a tree can drastically reduce the computational overhead of prefix searches. When evaluating the trade-offs of the different approaches, we can see why the tree-based solution stands out. The brute force method, while simple, is far too slow for larger inputs due to repeated full list scans. Binary search improves efficiency, but managing indices and ranges adds complexity, and it doesn't inherently limit the product lists to 3 items during pre-processing. The tree, on the other hand, preprocesses the products list in a way that ensures fast and accurate prefix searches, returning only the top 3 suggestions. This balance of preprocessing time, search efficiency, and scalability makes the tree the ideal choice for implementing the search suggestions system. Under the given constraints, the tree-based approach provides the best trade-off between time complexity, space complexity, and practical usability, making it the most efficient and scalable solution for this problem. To solve the problem of providing search suggestions as a user types, we start by understanding the inputs and outputs. The input consists of a list of product names and a search word. Our output will be a list of lists, where each inner list contains up to 3 of the lexicographically smallest product names matching each prefix of the search word. The brute force approach begins by sorting the product list. Sorting is crucial because it ensures that any matches we find for a prefix are already in the desired order, eliminating the need for repeated sorting. After sorting, we iterate through the prefixes of the search word, starting with the first character and progressively including more characters. This prepares us to find matches for each prefix systematically. For each prefix, we extract it by slicing the search word up to the current index. Then, we compare this prefix with every product in the sorted product list. If a product starts with the prefix, we add it to a temporary list of matches. This can be done using string slicing or Python starts with method, which makes the check straightforward. Once we have the list of matches, we select the first 3 products from it. If there are fewer than 3 matches, we take all of them. These top 3 results are then appended to our final results list. After processing all the prefixes, we return the results, which contain the best matches for each prefix of the search word. This approach, while simple, ensures correctness by systematically checking every product for every prefix. Returning the final results completes the brute force algorithm. Now, let's delve into some of the key insights from this approach. First, sorting the product list up front is efficient because it ensures that any matches we find are already in lexicographical order, saving us from additional sorting during each prefix check. Next, extracting prefixes from the search word is an efficient operation, as slicing a string is linear in the length of the prefix. Additionally, we can optimize the matching process by stopping once we find 3 matches for a prefix, reducing unnecessary comparisons. However, there's a trade-off between time and space efficiency here. The brute force solution doesn't require extra data structures beyond the results and temporary lists, but it does involve iterating through the product list multiple times, which can be computationally expensive for large inputs. Analyzing the complexity of this approach, sorting the product list initially takes n log n, where n is the number of products. For each prefix of the search word, we check all products, leading to m*n comparisons in the worst case, where m is the length of the search word. Combining these, the overall time complexity is n log n plus m*n. Now, let's walk through an example to understand how the algorithm works step by step. Given the input products as mobile, mouse, moneypot, monitor, mousepad, and the search word mouse, we first sort the product list. This results in mobile, moneypot, monitor, mouse, mousepad. For the first prefix, m, the matches are mobile, moneypot, and monitor. These 3 are added to the results. For the next prefix, mo, the matches remain mobile, moneypot, and monitor, so they are added again. For mao, the matches are now mouse and mousepad, and these are added to the results. The same matches, mouse and mousepad, are also added for the prefixes mouse and mouse. Therefore, the final output is mobile, moneypot, monitor, mobile, moneypot, monitor, mouse, mousepad, mouse, mousepad, mouse, mousepad. While this approach is straightforward and ensures correctness, its performance can be improved, especially for larger product lists or longer search words. This sets the stage for exploring more optimized solutions. Here, we define a class called solution and implement the suggested products method. The goal of this method is to return a list of product suggestions for each prefix of the search word, where the suggestions are sorted lexicographically and limited to 3 per prefix. First, we sort the products list to ensure the suggestions appear in the correct order. We then initialize an empty result list to store the suggestions for each prefix, and a prefix string to build the search prefixes dynamically. As we iterate through each character in the search word, we append the character to the prefix and use a helper method, binary_search, to find the starting index of products matching the current prefix. From this starting index, we collect up to 3 products that begin with the prefix and add them to the result list. Finally, the result list, which now contains suggestions for all prefixes, is returned. The binary underscore search method, defined separately, helps us efficiently locate the starting index for products that match a given prefix. The binary underscore search method is designed to efficiently locate the starting index of products that match a given prefix using a modified binary search algorithm. We initialize 2 pointers, left and right, to represent the search space within the sorted products list. While the left pointer is less than the right, we calculate the midpoint and check whether the product at mid is lexicographically smaller than the prefix. If it is, we narrow the search space to the right half by setting left to mid +1. Otherwise, we reduce the search space to the left half by updating right to mid. Once the loop exits, left will point to the index of the first product that matches the prefix, which we return. This method ensures that we find the starting index in logarithmic time, making the solution efficient even for large product lists. Here, we begin by importing the necessary utilities and defining our solution class. The main method, suggested products, takes in an array of product names and a search word. First, we sort the products lexicographically to ensure that any suggestions we generate are in the correct order. Then, we initialize a result list to store the suggestions for each prefix of the search word and use a string builder to progressively build these prefixes, 1 character at a time. For each character in the search word, we append it to the prefix and convert it to a string. Using this prefix, we determine the starting index of potential matches by calling the binary search helper method. Next, we iterate over the products, starting from this index, and add up to 3 products that match the prefix to our suggestions list. Once the suggestions for the current prefix are ready, we add them to the result list. This process repeats for every prefix of the search word, ultimately returning all the suggestions for each step of the search. The binary search method is a helper function designed to efficiently find the starting index of products that match a given prefix. It takes in the sorted array of products and the prefix to search for. Using a standard binary search approach, we initialize 2 pointers, left and right, to define the search range. While the left pointer is less than the right, we calculate the middle index and compare the product at this position with the prefix. If the product at the middle index is lexicographically smaller than the prefix, we move the left pointer to mid +1, effectively narrowing the search to the right half. Otherwise, we adjust the right pointer to mid, focusing on the left half. Once the loop terminates, the left pointer represents the smallest index where products starting with the given prefix could be found. This index is then returned to the main method, enabling it to gather matching products efficiently. To solve this problem, we begin with the input products array and the search word. The first step is to sort the products array alphabetically. Initially, the products are mobile, mouse, moneypot, monitor, mousepad. After sorting, they become mobile, moneypot, monitor, mouse, mousepad. This sorting ensures that suggestions will always be returned in lexicographical order. Next, we initialize an empty list called result to store the final output and a variable prefix to build the search prefix character by character. Now, we start processing each character in the search word, which in this case is mouse. For the first character M, we update prefix to M and perform a binary search to locate the starting point of products that match this prefix. The binary search narrows the range by repeatedly comparing the middle element of the current range with the prefix. Here, the process leads to a starting index of 0. From this index, we collect up to 3 suggestions, which are mobile, moneypot, monitor. These 3 suggestions, mobile, moneypot, monitor, are then appended to the result list. Moving to the next character in the search word, which is O, we update prefix to MO. The binary search is called again to find the starting index for this updated prefix. The search narrows down as follows. First, the middle product is monitor, which is greater than or equal to MO. This narrows the range further until we determine the starting index is still 0. From this position, we again collect up to 3 suggestions, which remain mobile, moneypot, monitor. These are appended to the result list. By maintaining the order of the sorted array, we ensure that the suggestions remain consistent for prefixes that share the same starting products. At the third character, U, the prefix becomes MAU. The binary search now determines that the starting index has shifted due to the updated prefix. Initially, the middle product monitor is less than mul, so the left boundary is adjusted. The search continues until it identifies the starting index as 3, where the product matches the prefix. From index 3, we collect up to 3 suggestions, which are mouse, mousepad. These are then appended to the result list. The same steps are repeated for the next 2 characters, S and E, resulting in prefixes mouse and mouse. For both of these, the binary search identifies the same starting index of 3, and the collected suggestions remain mouse, mousepad. By the end of this process, the final output for this example is mobile, moneypot, monitor, mobile, moneypot, monitor, mouse, mousepad, mouse, mousepad, mouse, mousepad. Now let's look at another example with the products dog, deer, deal, and the search word D. The process begins by sorting the products alphabetically. Initially, they are dog, deer, deal, and after sorting, they become deal, deer, dog. With the sorted array, we initialize the result list as empty and prefix as an empty string. For the first character in the search word, D, we update prefix to D. Performing a binary search for this prefix, we narrow the range until the starting index is identified as 0. From this position, we collect up to 3 suggestions, which are deal, deer, dog. These are appended to the result list, providing the first set of suggestions for this example. For the next character, E, the prefix updates to DA. We perform another binary search for this prefix. The narrowing process results in the same starting index of 0. From this position, we collect up to 3 suggestions, but since only 2 products match the prefix, the suggestions are deal, deer. These are appended to the result list. With no more characters to process in the search word, the final output becomes deal, deer, dog, deal, deer. This demonstrates how the algorithm efficiently narrows down the search space and collects suggestions for each prefix using binary search and a sorted product list. To analyze the time complexity of our solution, we can break it into distinct components. First, we sort the products list lexicographically. Sorting requires O, M** log, M, time, where M is the number of products in the list. This is a one-time operation performed at the beginning. Next, we iterate through the search word, which has a length of n. For each character in the search word, we build a prefix incrementally. This means we perform n iterations to process the entire word. For each prefix generated, we use binary search to locate the starting index of products that match the prefix in the sorted list. Since binary search operates in O, log em, time, and we perform this search for n prefixes, the total cost of binary search operations is O, n** log em. These steps together characterize the major components of the time complexity for this solution so far. After identifying the matching range of products for a prefix using binary search, the next step is to collect up to 3 matching products to serve as suggestions. This involves iterating through at most 3 products, which is a constant operation, O(1), for each prefix. Over n prefixes, this contributes an additional O, n, to the total time complexity. Now, combining these components, sorting the products list, iterating through prefixes, and collecting suggestions, the overall time complexity becomes O, M** log m for sorting, O, n** log m for binary search over all prefixes, and O, n for collecting suggestions. When we combine these terms, the total complexity is O, M** log m plus n** log m plus n. For large values of m and n, the sorting and binary search terms dominate, so the time complexity simplifies to O, M** log m plus n** log m. Let's now focus on the space complexity of the solution. First, we consider input storage. The products list contains m strings, and since no additional copies are made, the space required for input storage is O, m. Next, the prefix string is built incrementally as we process each character of the search word. In the worst case, the prefix string will store the entire search word, which has a space requirement of O, n. Additionally, the result list stores the suggestions for each prefix. Each prefix can store up to 3 products, so for n prefixes, the total space required for storing results is O, 3*n, which simplifies to O, n. Finally, the binary search operates in place on the sorted products list and does not require additional memory. These components together form the overall space complexity. When we sum up the space requirements, we get the following: O, M for input storage, O, N for the prefix string, and O, N for the result list. Therefore, the total space complexity of this solution is O, M plus N. To understand the efficiency of this approach, let's compare it with a brute force solution. In a naive approach, we would check every product for each prefix to see if it starts with that prefix. This would take O, M, time per prefix, and with N prefixes, the total time complexity becomes O, N asterisk M. This is significantly less efficient compared to the optimized solution, which reduces the product search time to O, log EM, per prefix by leveraging sorting in binary search. As a result, the optimized approach is far more scalable, especially when M, the number of products, is large. Finally, let's analyze the best, average, and worst-case scenarios for this solution. In the best case, all products start with the same prefix. Here, binary search quickly identifies the range of matching products. However, since sorting still takes O, M asterisk log EM, and binary search and prefix processing contribute O, N asterisk log M, the overall complexity remains O, M asterisk log M, plus N asterisk log M. In the average case, the performance is similar because sorting and binary search dominate the cost. Even in the worst case, where all products are distinct and no common prefixes exist, the sorting and binary search operations remain unchanged. This means the overall complexity is still O, M asterisk log M, plus N asterisk log M, consistently efficient regardless of the input distribution. When solving the search suggestions system problem, there are a few common mistakes to watch out for. First, not sorting the products list lexicographically before searching for matches is a frequent oversight. This sorting step is critical because the output must always present suggestions in lexicographical order. Without it, the results won't meet the problem's requirements. Another frequent issue is inefficient prefix matching. For example, using nested loops to examine every product for each prefix can lead to O, N squared, or worse time complexity. This approach becomes impractical for larger input sizes, such as when the number of products reaches 10,000 or more. Lastly, it's important to handle edge cases properly. Solutions that fail to address situations where no products match a prefix, search word is empty, or the products list itself is empty may produce runtime errors or incorrect results. Ensuring your solution accounts for these scenarios is essential for robustness. Now, other inefficiencies can arise from the choice of data structures. Using basic lists for prefix matching, for instance, can lead to redundant computations and unnecessary slowdowns. More efficient structures like tries can significantly optimize runtime by avoiding these redundancies. Another pitfall is hard-coding constraints. For example, assuming that the maximum number of suggestions is always 3 without explicitly coding for this can create issues if the constraints change or are misunderstood. From an interview perspective, this problem is a blend of string manipulation and efficient search. Interviewers often look for your ability to think critically about optimizing prefix matching, typically with data structures like tries or using binary search. It's also important to discuss spacetime trade-offs. While tries are memory-intensive, they provide O, M, prefix searches, where M is the prefix length. Always explain how you handle edge cases, such as empty inputs or no matches. Even if you start with a brute force approach, clearly communicate why it's inefficient and outline your plan for improvement. This problem is closely related to other string and prefix matching problems on LeetCode. For example, in LeetCode 642, you design a search autocomplete system, which is conceptually similar. LeetCode 208 focuses on implementing a tree, a key data structure for solving problems like this efficiently. Additionally, LeetCode 1268, the current problem, and LeetCode 720, which involves finding the longest word in a dictionary, all share overlapping techniques. When considering alternative approaches, a tree-based solution is a powerful option. By building a tree from the products list, you can retrieve matching products for each prefix in lexicographical order. This approach has a complexity of O, N asterisk L plus M, where N is the number of products, L is the average product length, and M is the length of search word. However, this comes with high space usage due to the tree structure. Alternatively, a binary search solution involves sorting the products list and using binary search to determine the range of matching products for each prefix. This has a complexity of O, n log n plus m squared asterisk log n, which is less space-intensive than a tree but can be slower for longer prefixes. Finally, there's the brute force solution. In this approach, you iterate through all the products for each prefix of searchword to find matches. It has a complexity of O, m asterisk n, where m is the length of searchword and n is the number of products. While this method is simple to implement and easy to understand, it becomes highly inefficient for larger inputs. For example, if the number of products is very large, the runtime will grow quickly, making it unsuitable for competitive coding or interview scenarios. This simplicity, however, can make it a good starting point for understanding the problem before refining your approach with more optimized techniques like tries or binary search. Thank you for joining. We've successfully tackled the search suggestions system problem, breaking down key approaches and their complexities. I hope you've gained valuable insights into string searching techniques and algorithm optimization. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!